Hello. In our last lecture, we have learned various rate laws, then concentration time equations, then their half lives. Like for zero order reaction, rate was found to be equal to k. I mean, just for zero order rate equal to k. Then for first order, rate is equal to k times a. For the second order, rate is k times a to the power 2, and corresponding half lives are like this, where you see that for the first order reaction T half is independent of the initial concentration of the reactant. Now, next we will move on to a special kind of reaction which is called the pseudo first order reaction. Pseudo first order reaction. Pseudo first order. So, the kinetics of complex reactions may be simplified, and rate laws become easier to use. Although, in certain cases some complicated rate laws may happen, but under certain simplification those rate laws may be reduced down to some usable form. Suppose we are having a reaction of this sort, CH3 COO C2H5, that is ethyl acetate in water in presence of maybe little trace amount of acid producing acetic acid and ethyl alcohol C2H5 OH. So, it is in true sense a second order reaction, that is rate is proportional to the concentration of this and also concentration of water. Okay. Now, this reaction is carried out in water, that is you put a measured amount of ethyl acetate in a given volume of water, then you add a trace amount of a little amount of acid, say HCl, and then allow the reaction to proceed. So, in that case ethyl alcohol and acetic acid will be formed along with water. I mean water will remain as it is, that is suppose we have used say 100 ml of water and we have put say 1 ml of ethyl acetate. So, all 100 ml of water will virtually remain remain 100 ml, although very little amount of water will be used up to decompose this one, but virtually the water concentration will not change. That means, since the water concentration, that is the one of the reactants is kept at high value, then virtually it does not change appreciably. Okay. So, now in that case a second order rate law may be simplified, and this will reduce to a first order reaction, I mean first order kinetics, and this generally holds one or more reactants constant by employing high concentration. So, if we put this one high concentration, then throughout the reaction we may think that this is virtually constant. So, a pseudo first order reaction, say general start from a general second order reaction, that is A plus B, say this is A and this is B, A plus B producing products. So, your rate expression will be dx dt is equal to K 2 is for the second order one, is equal to, I already have talked about this expression, it is a general second order expression, minus x times B naught minus x. Okay. So, now if B is held constant, then if this is held constant, or maybe if it is kept at some high value, then for all practical purposes we can think that this one, that is this second quantity, bracketed second quantity, is constant. So, that means in that case this expression reduces to dx dt is equal to K2 AB is equal to K2 A naught minus x times B naught, because it is in high concentration or in large excess. So, during the course of reaction A reduces, but B remains almost constant, So, now if we plot this one, the plot will look like a first order one. That means, rate will now be written as your K2 then B naught times A naught minus x. So, the plot will look like a first order plot. Okay. So, now we will move on to certain examples, simple example. Okay. So, let us concentrate on to a reaction of this kind, say 2 Fe 3 plus aqueous, means aquated ion plus SN2 plus, this is also aqueous, producing 2 Fe 2 plus aqueous plus SN4 plus aqueous. Okay. And we would like to know the rate of formation of Fe2 plus, that is the ferrous iron. So, we need some time information. So, say let us put t is equal to say 40 second and say concentration of Fe2 plus, say this is equal to 0.0015 molar. We can measure by various means, maybe spectrophotometrically or maybe some other analytic method, we can measure the concentration, and t is equal to 0 to t is equal to 40. So, delta t is equal to 40 second, and so delta Fe2 plus is equal to 0.0015 minus 0, because why this is 0? Because at the start there was no Fe2 plus. So, this much of molar. So, rate of formation of Fe2 plus is equal to delta divided by delta t, which is equal to 0.0015 divided by 40 second, and this is molar, and this gives you 3.75 into 10 to the power minus 5 mole second inverse. So, this way we can find out the rate of formation of Fe2 plus. Next is about the stoichiometric equation. Say let us have a concrete example, 2 Fe3 plus aqueous SN2 plus aqueous giving rise to 2 Fe2 plus aqueous plus SN4 plus aqueous. Then rate will be equal to delta of concentration of SN4 plus by delta T, which is equal to half delta of concentration of Fe2 plus by delta T, which is equal to minus half, because it is 2, this stoichiometric coefficient half, therefore, delta of Fe3 3 plus divided by delta of T. So, this way we can write, because we can express rate in this way, that time rate of change of concentration of SN 4 plus, because at 0 time there was no SN 4 plus. Therefore, your whatever SN 4 plus is formed is the net SN 4 plus formed. So, from that we can find out the rate. In the same way, we started with Fe 3 plus, but initially there was no Fe 2 plus. So, again in the same way your initial Fe 2 plus is 0. So, from that we can find out the rate of formation of Fe 2 plus or the rate of formation of Fe 3 plus, and from that overall rate of reaction. Next we will move on to experimental measurement of chemical reaction rates. Okay. So, let us start with a simple example, that decomposition of H2O2 producing 2 H2O liquid, because it happens in aqueous H2O2 plus O2 gas is evolved. So, how to find out the rate? Now, in this case, suppose that this gas so evolved is behaving ideally. So, in that case we can use the ideal gas equation, that P v is equal to N R T. So, that is P is equal to N by V R T. Okay. So, N by V means it is basically concentration of O2, because no gaseous species is there on the left hand side. So, only on the right hand side this oxygen is the gaseous species. So, O2 then R T. Okay. So, that means concentration of O2 is equal to P by R T. Okay. So, rate will be equal to delta O2, delta of concentration of O2, because delta O2 means how much of change in concentration of O2 is there, divided by delta T. So, basically delta O2 is nothing but O2, because at the very start there was no O2. Okay. So, at T is equal to 0, concentration of O2 is equal to 0. That is why it will be delta P by R T into 1 by delta T. Okay. Delta P means change in pressure. Okay. Change in pressure. So, if we measure change in pressure as a function of time, okay, we should be able to find out the rate of reaction and the corresponding other parameters involved. Okay. Other parameters means rate, then rate constant, although it is a constant quantity. So, these things, and also we should be able to find out the proper plots and etcetera, so on and so forth. So, just by measuring the delta P and delta T, we should be able to find out the rate of this particular reaction. Now, if we would like to know the concentration of H2O2 after the reaction has elapsed say 10 seconds, how to find out? How to find out the concentration if we are given the initial concentration? So, again we start with the same reaction, H2O2 liquid producing H2O liquid, or it is better to say aqueous liquid plus half O2 gas. Okay. So, in that case we would like to find out the concentration of H2O2 after 10 seconds. So, let us think that initial concentration is given to be is equal to say 1.16 molar, and also given that rate is equal to 8 into 10 to the power minus 4 mole second inverse. Okay. So, which is equal to minus of delta H2O2 divided by delta t, y minus because it is depleting. Okay. So, we can write from this, we can write minus of delta H2O2 is equal to minus of H2O2 final minus H2O2 initial, which is equal to 8 into 10 to the power minus 4 mole second inverse into delta t times delta t. Okay. So, from this again we can write H2O2 10 second minus 1.16 molar is equal to minus 8 into 10 to the power minus 4 mole second inverse into 10 second. So, this gives you H2O2 10 second is equal to 1.16 molar minus 0.008 molar, which is equal to 1.152 molar. So, that means after 10 seconds the concentration of H2O2 which is remaining in the solution, that is which has not taken place which has not taken part into this decomposition reaction is 1.152 molar. So, that means it has reduced in 10 seconds, it has reduced to a little bit, but it has reduced because of this chemical reaction which is nothing but the decomposition process. Now, there is another method which is called the initial rate method. Initial rate method to find out the rate of reaction. Now, let us look into this slide, that here we are using the same reaction, that is H2O2 aqueous producing H2O liquid and 0.5 O2 gas. Now, and this is the concentration of hydrogen peroxide as a function of time. So, these dotted points, I mean this one is one data, this is another data point, this is another data. These are the data points. The square black squares are your data points. So, you see that it is reducing with time. Now, if we draw a tangent at some specific point, say at this point, and then another tangent at this point. So, this tangent is basically the rate, that is rate of delta H2O2 divided by delta T. It is giving you this one. So, basically this slope, this is the slope. Okay. So, this slope is basically how much? This slope is basically this 2.3, this value is 2.3 and this value is about 1250. So, if you divide this divided by 1250, then you will be getting some number which is 1.84 into 10 to the power minus 3 mole per second. So, this number at this particular the tangent has the magnitude 1.84 into 10 to the power minus 3 mole per second at this point, and here it is 6.54 into 10 to the power minus 4 mole per second at this point. Okay. So, we are just looking into or looking at the concentration versus time plot and the corresponding slopes. Okay. And rate is nothing but your del T of concentration of H2O2. So, we would like to find out that. Okay. So, basically we have this plot and on top of that we have got this slope. So, for this one this value is 1.8 and this value is about 2750. So, that is why 1.8 by 2.2750. Okay. So, so how to employ this method in finding out your rate of reaction along with the order of a reaction. So, we are just interested in finding out the order of reaction employing the initial rate method. So, from this initial rate we just wanted to know what is the rate at that particular instant. So, at this instant the rate is this much, I mean this much, at this instant this rate is this much, because as we move on towards longer time scale, reactant amount of reactant is reducing, therefore, the reaction rate becomes sluggish, therefore, the slope is reducing. Okay. So, we would like to use this information in finding out the order of a reaction. Okay. So, we are using say this reaction, mercuric chloride oxalate producing chlorine gas and then carbon dioxide and mercurous chloride. So, we are using 3 sets for this particular example. So, set 1 where mercuric chloride is 0.1 molar, oxalate is 0.1 molar, set 2 it is mercuric chloride is 0.1, oxalate is double of set 1, it is 0.2, and the third set is mercuric chloride is 0.05 and the oxalate is 0.2, and the corresponding initial rate, I mean slope of the concentration versus time plot, it is like for this set 1 it is this much 4015, here it is 4061 for the set 2, and for the set 3 it is 4029. We see that there is a definitive change of the initial rate as we move on to different sets consisting of different composition of mercuric chloride and oxalate. Okay. So, so again we use this expression rate for set 3 is equal to rate constant, then basically this reaction rate we do not know exactly the rate with respect to mercuric chloride and the rate with respect to oxalate. So, we have to write like this, rate is equal to K into HgCl2 to the power m and C2O4 2 minus to the power n. Okay. So, that means the reaction is mth order with respect to mercuric chloride and nth order with respect to oxalate. Okay. So, let us use set 3. So, set 3 is K is K into HgCl2 set 3 to the power m times C2O4 2 minus set 3 n. Set 2 for set 2 rate set 2 is equal to again K, the same rate constant HgCl2 set 2 to the power m, then this is ox means oxalate set 2 to the power n, which is equal to now we will use information about different composition and compare their relative proportion. So, you see that for set 3 and set 2 we are looking into set 3 and set 2. So, for set 2 the mercuric chloride is how much? It is twice set 2, it is twice set 3, yes sorry, it is twice set 3. So, that means 2 times HgCl2 set 3 to the power m times oxalate set 3 to the power n. Okay. So, now we divide this by this or set 2 by set 3. So, R 2 by R 3, that means R for rate for set 2, rate for set 3, which is equal to K times 2 HgCl2 3 means set 3 to the power m, then oxalate ox 3 to the power n divided by same K, then HgCl2 3 to the power m ox n 3. So, these 2 will cancel, again these 2 will cancel, K you will cancel. So, this will be giving you 2 to the power m. Now, we know what are the values of these initial rates. You see that R 2 is equal to 0.4061 and R 3 is 0.000029. So, it is approximately 2, that means equal to 2, approximately very close to 2. So, therefore, we can write from these we can write m is equal to 1. So, now we are now able to find out the value of m, that is the order with respect to HgCl2. We see that it is the first order with respect to HgCl2. So, the reaction which we are talking about, that is the reaction between HgCl2 and oxalate. In this case, this reaction is first order with respect to HgCl2. Now, we have to find out the order with respect to the other reactant. Okay. So, in that case we have to use other two option like say R 2, which is equal to K, then HgCl2 to the power 1, because now we are writing 1 because we already have found out that it is first order with respect to HgCl2, then OX 2 to the power n, which is equal to K into 0.1 into 0.2 to the power n, because it is 1. Okay. In the same way, R 1 is equal to K HgCl2 1 to the power 1, then oxalate 1 to the power n, which is equal to K into 0.1 to the power 1 and 0.1 to the power n. So, if we divide R 2 by R 1, we will be getting K into 0.1 to the power 1, 0.1 to the power n, sorry 0.2 to the power n divided by K 0.1 to the power 1 and 0.1 to the power n. Okay. So, and this is basically how much. If we look into the ratio for 2 and 1, it comes out to be equal to 4, because this is 0.000061 divided by 0.000015, that means it is basically 4. So, that means we cross out this 2. So, that means it is 2 to the power n, 2 to the power n is equal to 4, implies 2 to the power n is equal to 2 to the power 2, that means n is equal to 2. So, what we got at the end is very simple and is very informative, that your reaction rate, which is equal to K into HgCl2 to the power m and oxalate n is equal to, we can write HgCl2 to the power 1 and ox to the power 2. Okay. So, it is first order with respect to mercury chloride and second order with respect to oxalate. Okay. So, therefore, what is the overall order? Overall order is 2 plus 1 is equal to 3. Again you see that although your chemical reaction was like 2 HgCl2 plus oxalate producing 2 Cl2 plus 2 CO2 plus Hg2Cl2, but you see that your rate equation, it is first order, here it is stoichiometry 2, it is second order stoichiometry. So, there is no direct correlation between the stoichiometry and the order of reaction, order of with respect to a certain component. Next, we are looking at another example to find out X and Y. I mean, say it is a persulfate iodide reaction, where persulfate is an oxidizing agent and it oxidizes iodide to iodine, okay, and producing Ki3. So, it is a reaction S2O8 2 minus plus 3 I minus producing 2 SO4 2 minus plus I3 minus, okay, all are in equated form. So, we have got, if we look into your various set, you see that set 1 where persulfate is 0.07 molar and iodide is 0.03 and initial rate is 2.1 into 10 to the power minus 4. For set 2 it is 0.7 for persulfate, 0.07 and it is 0.015 for iodide and 1 into 10 to the power minus 4 for initial rate, and for the last one it is for persulfate it is 0.14, for iodide it is 0.015 and the initial rate is 2.1 into 10 to the power minus 4. Okay. So, rate we can write in general equal to K into S2 2 minus to the power x and I minus to the power y. Okay. So, if we look into the data, you see that doubling I minus doubles the rate. If we double I minus, you see, if we double I minus from here to here, you see the rate is doubled. Okay. So, from set 2 and 1 we see like this. So, that means we are keeping the concentration of persulfate fixed and we are just looking into the dependence, how it is depending, whether it is linearly dependent or it depends in some non-linear way. You see that it is doubled, it is also doubled. That means we can say for sure that this power should be 1, otherwise if it is more than 1 or something else than 1, then it should not have increased to the same extent, like it is double, it is also doubled. Okay. So, that is one thing. So, we are now able to find out that y is equal to 1. Now, what about x? You see here in these two cases 2 and 3, these two are remaining same. So, we are now looking at the effect of change of concentration of persulfate. It is that you see that it is 0.07, it is double to 0.14 and you see that the initial rate is doubled. That means, again in the same way we can say that for persulfate this y, I mean x is 1. Okay. So, that means it is nothing but K into S2O8 2 minus to the power 1 and I minus also to the power 1. Okay. So, and also K will be equal to rate divided by S2O8 2 minus times I minus, it is basically 2.1 into 10 to the power minus 4 divided by 0.707 times 0.03 mole square and this is mole second. So, this gives you 0.1 per mole second. Okay. So, this way we can find out, we can look into the rate law, we can find out the rate law and also the rate constant for a given reaction. There is another example of T half, that sugar is fermented in a first order process, okay, in a specific way, okay, where it has been found that rate sugar reaction is fermentation. Producing other chemicals. So, rate is equal to K times sugar to the power 1. It is known to proceed via first order kinetics and where K is equal to 3 into 10 to the power minus 4 second inverse. So, what is the half life of the reaction T half? Okay. So, since it is a first order process, therefore, T half will be equal to 0.693 by k, which is equal to, if we plug in the appropriate numbers, we will be getting 2310 second. So, half life is 2310 second. So, our next slide is reversible reactions. So, if equilibrium is far off, that is there is a little reaction in the opposite direction, that is very little reaction in the back direction, then we see a net forward kinetics. That means, there is no effect of the back reaction, even if there is a very little back reaction, but we do not see any effect of that. So, so that means we say that the equilibrium is far off and the reaction is forward direction shifted, that is forward shifted, or the right hand direction shifted. But if we think of a reaction like this, where it is not far from equilibrium, maybe close to equilibrium, there is a net back reaction, and if both the directions are in both the directions, the reaction is of first order kinetics, that is, it is a forward reaction, and say this is your reverse reaction, and corresponding rate constant K f, and this is K r. Then what can you write? That forward reaction, rate of forward reaction, rate of forward reaction, rate of forward reaction, this can be written as ddt of A is equal to K f into A. In the same way, rate of reverse reaction, it is ddt of B is equal to K r into B. Since I already have told you that in both the directions, kinetics is first order kinetics. Okay. It may be in other cases, maybe complicated situations are there, where forward reaction is following a second order kinetics and back reaction is a first order kinetics, or maybe second order is opposed by a second order, like that. Opposed means in the reverse direction is also a second order reaction. So, what is happening at equilibrium? At equilibrium, virtually there is no change in concentration. That means if we consider a particular constituent, like say A or maybe B. So, with time there is no change in concentration of A or maybe the concentration of B, if equilibrium has reached, has been attained. Okay. So, at equilibrium, what we can write? So, equilibrium, at equilibrium, forward rate forward is equal to rate reverse. Okay. So, we can write K f into A is equal to K r into B. Okay. So, equilibrium constant, there is a in this slide there is a little typo, actually K equilibrium will be concentration of B divided by concentration of A, this one, actually there is a typo, this one should be here and B should be here anyway. So, just correct it. So, so basically let me do it here. So, B, concentration of B divided by concentration of A is equal to K f by K r, which is equal to K equilibrium, concentration equilibrium constant, of course at a given temperature, because it is very much sensitive to temperature. Why? As I I will be coming to that later on, the effect of temperature, because you will be seeing that if you change the temperature of a reaction, it enormously affects the overall rate. Okay. So, that is why it is a very much temperature dependent quantity, this equilibrium constant. So, reversible kinetics, if for a simple first order opposed by first order kinetics, then you can write kinetics of reversible reaction, in that case requires a back reaction. I mean, back reaction means it is a considerable amount of back reaction. Otherwise, if the back reaction is not in considerable extent, then you will be seeing a net forward kinetics. Okay. So, that means for a reversible reaction you need to have a considerable amount of back reaction. So, there is a definite role that approach to equilibrium plays on overall forward reaction kinetics. Next, a little more complicated situation, that is first order consecutive reactions, that is A to B to C, that is A producing B, then B is producing C. Okay. So, here it is generated, B is generated, and then from B C is produced means C is depleted. So, it is an increasing function, basically with time it builds up and with time it depletes. That means you will be seeing, maybe I will come to that maybe later on, that you will be finding that this B will pass through a situation of maximum concentration with at a specific time, and then again it will deplete, because it is an increasing decreasing kind of thing. So, it should pass through an extremum anyway. So, that is some more involved description. So, you see that for the first step, that is Ka dNA dt, that is number of moles of A changing with time is minus Ka Na. dNB dt means it is produced and it is depleted. So, that is why it is a negative sign, and dNc dt, it is rate of change of rate of depletion or whatever, rate of change of C with time is Kbnb, because this is the step which is responsible for the depletion, formation of C. This is basically formation of C, not depletion, it is the formation of C. Okay. So, complications may come into action if we keep on adding more steps. Like this was the simplest situation we started with, then we have added another component, that B will be converted to C. So, you see that your description becomes more complicated. So, more complicated reaction we will talk about in later time. Okay, like it is a consecutive reaction, maybe a parallel reaction, like there could be another situation, say A to B to C, it is a consecutive. It may so happen that this A is doing another reaction, A to P to Q. Okay. So, this is a parallel reaction, this reaction is a reaction, this is another reaction, parallelly these two are happening. So, this is again this puts further complication. Okay. So, these parts, these complicated complex reactions will take up later on. Now, we will come to, as I told you, that temperature has got enormous importance in chemical kinetics, in rate processes, because if you change temperature a little bit, it changes many things. Okay. So, the rate constant, of which we are very much interested in chemical kinetics. So, rate constant is very much temperature dependent, and this relation between rate constant and temperature was has got this relation has a very famous citation, that it is called Arrhenius expression, and where K is equal to A into exponential minus E A by RT. So, it is an exponential function of temperature. So, E A is an energy term, T is the absolute temperature, A is a pre-exponential term. Okay. So, you see, with increase of temperature, K increases exponentially, K rises exponentially. Okay, and you see from this that K is dependent on temperature. It is from experience. So, from experience we have been able to, means people or scientists have been able to arrive at this expression, and this has been tested for all the cases and found to be true that K follows an exponential dependence with temperature. Okay, so it always, I mean, temperature always increases the rate constant. If you increase the temperature, rate constant also increases. So, and this pre-exponential term, so it is generally independent of temperature. Now, it is also called the frequency factor. Frequency means, I mean, it came from the reaction, I mean, theory of reaction rate based on collision theory. So, collision theory will talk about theory of reaction rates later on. Okay. Now, if we differentiate this expression, I mean, K is equal to A exponential minus E A by R T. If we differentiate, then it comes out to be like d dt of ln K is equal to E A by R T square. Okay. So, if you take logarithm of rate constant and then you do derivative, it will give you this quantity. Therefore, if you plot ln K versus 1 by T, like if you take the logarithm of your original expression, then ln K is equal to ln A minus E A by R T. So, if you do this plot, I mean plot of this versus this, okay, then it will be giving you a straight line with a negative slope. So, in y axis there will be ln K, x axis 1 upon T. Okay. So, slope will be minus E A with a negative, so it is a negative slope E A by R. Slope will be minus E A by R, and the intercept, this is the intercept. Intercept this way means 1 by T 0 means it is a huge temperature which you cannot do experimentally. So, you can go maybe up to certain temperature, this is your maybe highest temperature that you can do the experiment in the laboratory. Okay, so, these are the values corresponding to different temperatures, and in this side temperature is minimum, okay, and then you do extrapolation, because you need to extrapolate, otherwise you cannot get ln A, because you cannot do real experiment with a very high temperature. So, after extrapolation you will be getting ln A. So, ln A will be giving you, I mean this will give you the pre-exponential term, or which is also called the frequency factor. Okay. So, from this introduction it is clear that if you change the temperature, it changes the rate constant significantly, but whether it will be significant or insignificant, that is determined by the slope. That means that is determined by this activation energy. So, when higher activation energy is high, then your slope will be steeper, like this. Okay. That means like this, maybe this. Okay. So, steeper slope when E A is more. Okay. So, that means this slope, whether there will be a significant you know effect of temperature on rate constant, that will be decided by the magnitude of activation energy. So, this is a very important quantity, energetic quantity, that determines, you know, when you increase the temperature, whether you will have a significant change in rate constant of the process. So, that is why we need to have a careful, you know, observation of observation on this E A value. This is very important. Carefully you have to observe every time for any reaction. When you study any reaction, then you have to be careful. You have to be careful in finding out this. This is a very important quantity. Okay, careful means why careful? I am telling you that this determines the very nature of your temperature variation experiment. Where if you change the temperature, then your K value will be modified. So, how it will be modified, that is decided by E A. Next is let us have a look at typical range of this activation energy, that is different. I have tabulated a number of processes, reactions with their typical range of activation energies. So, physical absorption means adsorption. Physical adsorption means basically adsorption is a surface phenomena. So, physical adsorption means there is no chemical linkage. Okay, there is no chemical linkage that happened between adsorbate and adsorbent, but there may be a physical force, maybe van der Waals force or maybe something else. Okay. So, so that has got typical range of EA 2 to 6 kilocalorie per mole. Aqueous diffusion means say you put some sugar in water and you do not agitate this the water, then maybe after some time you will be finding, after some time, maybe after a day, maybe you will be seeing that the whole water is now sweetened. So, this is basically because of the aqueous diffusion. So, that aqueous diffusion has got a typical range of activation energy less than 5 kilocalorie per mole, less than 5 kilocalorie per mole. Then biotic reaction, it is 5 to 20 kilocalorie per mole. Then mineral dissolution or precipitation. Mineral dissolution means say you are having some lump of mineral and then you leach with water, then maybe some of the minerals will get dissolved. So, this dissolution this dissolution has got typical range of activation energy 8 to 36 kilocalories per mole. Then dissolution controlled by surface reaction. Surface reaction means it is not a typical surface reaction, is a I mean the reaction which we generally do is a typical bulk reaction. Surface reaction means those reactions like zero order reaction, like dissociation of ammonia on gold surface, that is a surface reaction. So, this dissolution controlled by surface reaction has got 10 to 20 kilocalorie per mole. So, surface reaction is different from bulk reaction. So, and that requires about 10 to 20 kilocalories per mole. Isotopic exchange in solution phase, suppose you have got say ROH, alcohol, where hydrogen is hydrogen, and if you want to exchange that hydrogen with deuterium, then that isotopic exchange would require 18 to 48 kilocalorie per mole. Solid state diffusion in mineral, because this diffusion occurs in solid phase, so that requires more activation energy, and it is 20 to 120 kilocalories per mole. Okay. So, what we have learned in this particular part of discussion, that we have learned various we have learned like how to use initial rate method to find out the rate equation, that is you have got say rate is equal to k into say a to the power alpha b to the power beta. So, what is the value of alpha and beta, and to find out the overall order of the reaction. So, that you can do by making use of initial rate method. Okay. And also we have studied various types of kinetics like zero order, first order, second order, third order, and also nth order. Also we talked about the pseudo unimolecular reaction, where you have kept one of the reactants in large excess, so that virtually during the course of reaction it is not changing. So, the whole rate equation is now simplified to a one order less, or maybe a second order one is transformed to a first order one. And also we have talked a little about this reversible reaction, and also consecutive reaction. We gave a very brief introduction of consecutive reaction. So, in the next class, we will talk about the temperature effect, in details, and also we take up this Arrhenius equation, how this can be used, what is the utility, what is the significance of activation energy, what is the significance of this pre-exponential term. All will be taken up maybe in next 2 lectures on the effect of temperature on chemical reaction rate. So, till then have nice time. So, see you in next lecture with this effect of temperature on chemical reactions. Thank you.